Hello, my name is Gabriel Goria, and my project is car piston bearings for my material science class at Hartnell College. Piston bearings support the crankshaft, which is this long section in the engine, and it allows rotation for the pistons. They are typically made from cast iron and carbon steels. The piston bearings go into this section of the piston, which is then placed onto the crankshaft, and they are rotated up and down. I chose this topic because I wanted to know how pistons and bearings have long lifespans under high temperatures, constant movement, and thousands of cycles. The function was to support the crankshaft and allow rotation for the piston. My functional constraints was that the material needed to be strong enough, some hardness to withstand friction, have some toughness, have a high surface temperature, have a low enough thermal expansion coefficient to not deform, have high creep strength, and low coefficient of friction. My geometric constraints was the diameter specified and the cross-section area to fit inside the piston. My objective was to minimize cost, and my free variable was the choice of material. My general properties was to have a low cost. My mechanical properties was to have a high fatigue strength, low coefficient of friction, high creep strength, and high hardness. My thermal properties was to have a high maximum surface temperature, low thermal expansion coefficient. I wanted a processability of the material to be castable. My chemical properties was it to be corrosion resistant. And the family that was chosen are metal and alloys. From the screening, the material chosen were cast iron ductile nodular, cast iron gray, high carbon steel, medium carbon steel, and low carbon steel. Metals were chosen over ceramics because they were cheaper and also had a higher Young's modulus and had a higher fatigue cycle. My objectives from the rankings were to minimize cost and have a high Young's modulus. The equation of the slope was Young's modulus over price. And the top choices were cast iron ductile nodular, cast iron gray, high carbon steel, medium carbon steel, and low carbon steel. The winning material was cast iron ductile nodular. The cast iron ductile nodular had a high Young's modulus at around 170 to 180 gigapascals, was cheap at 0.355 US dollars per kilogram, had a high fatigue strength at 195 to 317 megapascals, and a high maximum surface temperature at 350 to 450 degrees Celsius. It was also very durable in many solutions, but especially in fuels and oils. Since it will be in the engine, it will have a lot of lubricating oil, and it is excellent at being durable in lubricating oils. My winning material had the lowest price to manufacture more for a lesser price, since there was a large demand of piston bearings. The material needed to be corrosion resistant to air and sulfuric acid, and they are coated with motor oil when they are inside the motor. It needed to be castable to manufacture a lot of them for cheap, and they are also recyclable. In conclusion, the winning material was cast iron ductile nodular because it was the cheapest, but also had a high Young's modulus and high fatigue cycle. My findings matched background and research in finding the objective. If I had had more time, I could have had more comparisons between materials and found out which material would have been better in each category. It was important to find a material that could be sufficient for the job at hand, and the error was that I could not show the low carbon steel on the graph because it was hidden behind the high carbon steel and the medium carbon steel. That is it for my project with car piston bearings, and hope you enjoyed.